So in this video, we're going to be looking at electron structure and how we can actually build on some ideas that we already know at GCSE and bring them up to an A-level standard, right? Now, first of all, if we were to look at electrons, we know they don't just move about anyhow. They actually move around in the atom in things called shells, right? And these shells can hold a certain number of electrons. Now, we might also refer to these as energy levels, right? And that's because when we look at distance, right, and when we look at the actual nucleus itself, the further an electron is going to be away from the actual nucleus, the greater its energy is going to be itself. And you can see this electron over here is going to be at a greater energy compared to this electron over here because it's further away. It's in a shell that's further away, so we say it's at a different energy level instead. Now at A level, we might also refer to the shell number as something called a principal quantum number, normally given the symbol n. And what we say is that if we're dealing with the first shell, right, we know the principal quantum number is going to be n is equal to 1, right? If I were to look at the second shell, it's going to be 2. If I were to look at the third shell, it's going to be 3, and then the fourth shell 4 itself as well. Now, one of the things that we could actually be asked at A level is to actually find the number of electrons in a given shell. And we can do this using the 2n squared rule, where we say n is equal to the shell number or the principal quantum number. So in this case, I've got an example over here where I'm asked how many electrons are found in the third shell of a bromine atom, right? And if I were to look at my equation again, to find the number of electrons in the shell, I'll just take 2 times it by the shell number or the principal quantum number squared itself, right? So in that case, I'm going to have my number of electrons in that third shell as being equal to 2 times by and then 3 squared. 3 squared is 9. 9 times 2 is going to be 18. So I know I've got 18 electrons in that actual shell itself, right? And there's my answer. I've got 2 examples, right, 2 common exam questions that I want you to have a go at. Feel free to pause the video and resume once ready to go over the answer. So yeah, the first question is asking us how many electrons are in the fourth shell of an iodine atom itself, right? So in this case, right, we need to think, okay, our 2n squared rule. So I know to find the number of electrons in the fourth shell, I'm going to have 2 times by our principal quantum number n, which is the same as the shell number, which in this case is going to be the fourth shell, so n is equal to 4 squared itself. 4 squared is going to be 16. 16 times by 2, that's going to give you 32 electrons itself. Yeah, so far nice and easy. Now in this example over here, we're told which shell contains 50 electrons. So again, thinking back to our 2n squared rule, we don't actually have a value for n itself, and that's what we need to find out, because we're asked about which shell that we're actually dealing with. We're asked about which principal quantum number that we're actually dealing with. So in that case, right, 2n squared is equal to 50, and I need to now rearrange this to get n on its own. So in this case, right, what I'm going to do, I'm going to divide by 2 on both sides to begin with, right? So I'll divide by 2 over here, and that leaves me with n squared being equal to 25, and then I'm going to square root both sides, and I'm left with n being equal to 5 itself. So we're dealing with the fifth shell itself as well. So we know our principal quantum number is equal to 5 in this case. Yeah. So moving on from that then, right, let's look at our shells in a bit more detail now. This is where we start to bring things up to an A-level standard. Now, when we look at the first shell, the second shell, the third shell, and the fourth shell, they can hold different amounts of electrons itself, right? And when we look at the first shell, right, we know that we can hold 2 electrons in there. If we were to look at the next shell, which is going to be the second shell, we can actually hold, right, 8 electrons in there. If I look at the third shell, we can actually hold 18 electrons in there. And then if I were to look at the fourth shell, right, I can hold 32 electrons in there. Now the thing is, within these shells, we have different subshells that make up the actual full shell itself. And these actually have different energies themselves. Now the subshells that we can actually get could be either S, it could be P, it could be D, or it could be F as well, which we normally show with lowercase letters in this case. If I were to look at, let's say, the first shell can have 2 electrons that can be arranged in the S subshell. If I were to look at the second shell, right, we can end up with 8 electrons. 2 of them can be arranged in the S subshell, and then the remaining 6 could be arranged in the P subshell. If I were to look at the third shell in this case, right, I can have again 2 in S, I can have 6 in P, and then I can have 10 in the D subshell itself. If I were to look at the fourth shell, right, I can have again S, I can have P, I can have D, and then comes F itself as well. And it's important to note that the S can hold 2 electrons, the P can hold 6 electrons, the D can hold 10 electrons, and then the F can actually hold 14 electrons itself as well. And that's our different subshells that we can actually get. If I've got the S subshell in all 4 of these, right, it can only hold 2 in each one, right? So you can have 2 in the first S subshell, 2 in the second S subshell, 2 in the third and the fourth as well. The same rules apply with the P subshell. You can only have 6 electrons in there, regardless if it's the second, third or fourth. D can only hold 10 in the third and the fourth and beyond, and then F can only hold 14 onwards as well. And you've probably noticed a bit of a pattern here, which some people can see, right? The greater the actual energy level itself, the more subshells you can get. In the first shell it's just S, in the second it's SP, in the third it's SPD, and then in the fourth it's SPDF itself as well. Now moving on, if we were to look at our subshells, we can actually further categorize our electrons now in existing in orbitals, because that's what they really exist in. And if you were to look at orbital, right, an orbital is just a region that can hold up to 2 electrons of opposite spin itself. Now these subshells themselves, they have a bunch of orbitals in them, and each orbital holds 2 electrons itself. But you need to think about it like this: if you've got electrons within the same subshell, we say that they have the same energy itself. Now, what does spin actually mean? Because I've mentioned spin quite a few times now, right? Spin is basically going to be a property of an electron, like how you've looked at the mass, like how you've looked at the charge. A spin is another property where you can either get an up spin or a down spin, otherwise known as plus a half or minus a half. And these electrons, right, you'll have one over here, which is going to be up spin. We show it using a half-headed up arrow. And then another one is going to be down spin, right? You show it using, again, a half-headed down arrow itself as well. And in order to fill 2 electrons within an orbital itself, right, we need to have them at opposite spins itself, right? So think about it like this, right? Remember your S subshell, that can hold 2 electrons. If you think about how many orbitals it's got, right, for 2 electrons, you're going to have 1 orbital, because 1 orbital holds 2 electrons. The P subshell, that has 6 electrons, and you can have 3 orbitals, because 6 divided by 2 gives you 3. You've got 3 orbitals that contain 2 electrons each. The D subshell, that's going to have 10 electrons that are going to be put into 5 orbitals itself. Again, 10 divided by 2 is 5. If you were to look at F, right, you've got 14 electrons and you've got 7 orbitals itself. Another way to think about it is, if you've got 7 orbitals, right, 1 orbital holds 2 electrons. 7 times 2, that gives you 14 electrons in total as a maximum that you can actually get yourself. So yeah, that's something that we need to remember, right, in terms of how many electrons we can get in each subshell, as well as how many orbitals we can actually get in each subshell as well. And don't forget your definition for an orbital. It's a region that can hold up to 2 electrons of opposite spins itself. Now these orbitals actually have shapes, right, and we only need to know about the S and the P orbitals. The S orbitals, we say they've got a spherical shape, so they're just a ball, right, and they're just going to be a sphere like this. We also need to be able to draw it as well. Now the shape of this orbital is going to be quite important, because it shows us where we expect to find these 2 electrons. So they're going to be whizzing around somewhere within this spherical shape itself, right, within this sphere itself. If I were to look at p orbitals, this is where it starts to get a bit more complicated, because if you think back to your p subshell, you can have 6 electrons, which I've just put as E minus there, and you can have them in 3 different orbitals itself. And those 3 different orbitals, they're going to have a dumbbell shape, which looks like this, right? And that dumbbell shape is going to be 1 orbital, right? And you're going to have, right, a orbital that looks like this, that looks like this, and that looks like this as well. And what we say is we've got the py orbital, we've got the pz orbital, and we've also got the p subscript x orbital itself. Now what that actually means is because we've got 3 orbitals, right, which all three of them have that dumbbell shape. They actually rest on a different axis itself. And let's say if you were to stick them all together, right, because you've got a dumbbell shape along the x-axis here, a dumbbell shape along the z-axis here, and a dumbbell shape along the y-axis here. If you were to stick them all together, let's say in another diagram, which I'm going to roughly draw now very quickly, where I've got the x, y, and I've got the z-axis as well. You've got your py orbital, which looks like this. Then you've got your pz orbital, which looks like this. And then you've got your px orbital, which looks like this in this 3D drawn graph itself. And altogether, they actually make the p subshell, right? So remember, you get 6 electrons, and 2 of them are going to be in each orbital. This entire thing over here is going to be 1 orbital, right? Not to mistake that for 2. So to summarize, right, what we've learned today is that we've got different subshells within our actual shells itself. And those subshells you can see, right, S, you get them in every single shell. If it's in the first shell, you call it 1S. If it's in the second shell, you call it 2S. If it's in the third shell, you call it 3S, and so on. P, right, you can only get that in shell number 2 and above. You can get, let's say, in the second shell 2p, third shell 3p, and fourth shell 4p itself. D is 3 and above, and then F is 4 and above itself as well. Our electrons are going to be put into these things called orbitals with up and down spin, where you end up with something that looks like this, and you're going to end up with different amounts of orbitals in the S, P, D, and F subshells themselves, right? And altogether, your total amount of electrons is going to be equal to all of the electrons in every single subshell, in every single orbital, added up all together. And if you were to look at it in terms of the number of electrons in each cell, those 2 electrons are organized in 1s as an orbital. Those 8 electrons are organized in 1s, 2s, and 2p. If you were to look at those 18 electrons over here, they're going to be organized in terms of 1s, 2s, 2p, 3s, 3p, 3d, and then those 32 electrons, they're going to be organized in 1s, 2s, 2p, 3s, p, D, 4S, P, D, and F as well itself. So moving on from that, let's look at how we can actually write the electron configuration or draw an energy level diagram on an electrons in a box diagram itself, right? Now, before we do that, we need to look at these 4 rules when displaying electron configuration. The first and most important one is that we fill our electrons from the lowest energy subshells first itself, right? We work our way up from S to P to D, from 1 to 2 to 3 itself as well. If we were to look at our electrons, they fill orbitals that are at the same energy unpaired first before they start pairing. For ions, we add or remove electrons always from the highest energy level or from the highest shell itself. And if we were to look at our 4s electrons, which are an exception, they're added first and removed first before 3D itself, right? So yeah, let's look at an example then, right? So we're asked to draw the energy level diagram, then the electrons in a box diagram, and write an electron configuration for a calcium ion. Now, thinking about calcium, right, we need to think what's a smaller number on our periodic table tile. How many electrons has calcium got? It's got 20 electrons in total. Because we're dealing with a calcium ion in this case, we know we've got calcium 2+. So in that case, we're going to have 2 less electrons. So we're not going to have 20 electrons. We're going to have 18 electrons itself as well. Now, if I were to start off, thinking back to my rules, I start off at the lowest energy level and I add an electron at the bottom here in 1s. The second electron goes over here, and then I'm going to move to 2s, where I add the third and fourth electron, and here's where it starts to get a bit complicated. On the p subshell, you can see I've got different orbitals now, right? You can see so far that I've had my electrons in an orbital, one being upspin and one being downspin. The order really doesn't matter. But when we get to our p subshell itself, our electrons, they will fill up unpaired first, they'll fill up singly first, and then they'll start to pair. So then you can see I'm pairing these up, and so far I've got 10 electrons over here. Now I've got 10 electrons, I've got 8 more electrons to fill. So again, I'm going to move to the next energy level, which is going to be 3s. I've got 11, 12 done over here, and then I've got 6 more electrons to add. Again, they're going to be unpaired, 1, 2, 3, 4, and then 5, 6 itself. So in total now I have 18 electrons, right? And you can see that's how we can actually draw an energy level diagram. What about an electrons in a box diagram, which could also be given in the exam itself? If you were to look at the electrons in a box diagram, it's just the same thing as an energy level diagram, but it's a lot faster and quicker to do, especially on multiple choice questions. And so let's say if I were to do the same thing over here again, right? I've got 1, 2, 3, 4, right? I'm going to fill up unpaired. So I've got 5, 6, 7, 8, 9, 10. And then I've got 11, 12. I need to make 18. That's going to be 13, 14, 15, 16, 17, and then 18 electrons in total. So now the next thing to do is to write the electron configuration in the written format. So starting off, I've got the first shell, right, which is going to be 1. And then I'm looking at the subshell S. That's going to be S. How many electrons have I got in there? I've got 2, so it's 1s2. I look at the next shell. I've got 2. Right, within that I've got 2 subshells, S and P. Let's start off with S. I'm going to have 2s, 2 electrons in there again, so it's going to be 2s2. Look at P. I'm going to have 2p. I'm going to look at that subshell. I've got 6 electrons in there, so I'm going to have 2p6. Look at the next subshell. I've got 3s, right? And then I'm going to have 2 electrons in there again. And then when I look at 3p, right, you can see that subshell is going to have 6 electrons in there itself. And that's how we can actually write our electron configuration in the written format itself, yeah? Moving on, right, if you were to look at, let's say, the next example, I want you to pause the video and have a go. So yeah, in this case, if we're dealing with sulfur, we've got 16 electrons in total because it's an atom. Don't need to add or remove any electrons from there. And again, we start off at the lowest energy and we start off unpaired and then we start to pair it, right? Because it's at the same energy level. If I were to look at the next one, I've got the second shell. So I'm going to have 1, 2 electrons there. And then the third shell, right, because I've got 4 electrons so far, I'm going to have 5, 6, 7, 8, 9, 10 electrons itself, right? So I've got 6 more electrons to fill. It's going to fill up unpaired, then paired for 3s. So I've got 12 electrons now. And then I've got 4 more electrons, 1, 2, 3. They're going to be unpaired, and then I'm going to pair this one over here. And the reason why we actually do this is because electrons, if you were to think of them as magnets, right, you put 2 negative charges next to each other, right, it's going to need quite a lot of energy to kind of stay next to each other because they're both negatively charged, compared to if you were to fill them up singly first in separate orbitals themselves, right? And that is due to something called electron pair repulsion, which we'll look at in a later topic. So yeah, I've got my energy level diagram done. I'm going to do the same thing in my electrons in a box diagram, and I end up with the following over here. What about my electron configuration, right? This time we'll look at our electrons in a box diagram. So in this case, in the 1s subshell, right, I'm going to have 2 electrons. 2s subshell, I'm going to have 2 electrons. 2p subshell, I'm going to have 6 electrons. 3s subshell, I'm going to have 2 electrons. I've got 4 electrons now in my 3p subshell, so I'll put 4 as my superscript itself, yeah? So moving on from that, right, let's look at the next task. Feel free to pause the video and have a go yourself. So yeah, again, we're looking at an oxygen atom in this case, and oxygen has 8 electrons in total, right? And if we were to look at those 8 electrons, we know that they're going to fill from the lowest energy level, and then it's going to increase to the higher energy levels as we progress our way through it. So in this case, I've got 1, 2, 3, 4, I've got 5, 6, 7, remember, the unpaired, and then I've got 8 itself there, right? So in that case, right, I end up with 8 electrons, and that's done quite quickly there. Electrons in a box diagram, 1, 2, 3, 4, and then 5, 6, 7, and then 8 itself, right? We've got one paired orbital, one paired set of electrons within one orbital in our 2p subshell itself. So in that case, our electron configuration is going to be 1s, and then it's going to be 2 because I've got 2 electrons in there, 2s, 2 because I've got 2 electrons in here as well, and then it's going to be 2p, and then it's going to be 4 because I've got 4 electrons in here as well. Moving on to the final example, again, feel free to pause the video and have a go. So in this case, we're dealing with a bromide ion, and the examiner only expects us to go up to an atomic number of 36, where we're dealing with something like krypton, right? Which, if we were to look at this noble gas configuration, it actually matches krypton. So in that case, I've got 35 electrons for bromine. I add an electron on because it's a bromide ion. It's in group 7, gains an electron to form bromide, and I end up with 36 electrons in total. So in that case, I'm going to count again. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is where it starts to get a bit tricky, because you'd normally think, okay, I'll move to 3D, but 4s is the exception. It's at a lower energy level compared to 3D. And if you think back to our rules, right, 4s, we fill it first and then we remove the electrons first compared to 3D itself. So in that case, right, I'm going to add my other 2 electrons in here, and then I'm going to start to fill the 3D subshell now. So I'm going to have, right, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and then I'm going to have 31, 32, 33, 34, 35, 36 itself. So overall, right, I'm going to have 36 electrons. Now my electrons in the box diagram is going to be pretty straightforward. It's just going to be all of them filled pretty much. But just remember, you can get higher energy levels and higher subshells compared to what you've got over here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So I've got 36 electrons there. Again, I've got one S2, because I've got 2 electrons in that S subshell. Same again for 2s. And then I'm going to have 2p with 6 electrons in there, 3s with 2 electrons in there, 3p with 6 electrons in there, and then I'm going to move to 4s itself as well, because you're sitting the A level, right? This is what you're expected to know, that 4s is at a lower energy level compared to 3D itself. So I'm going to go to 4s 2, so I've got 2 electrons in there, and then I'm going to come back to 3, and I've got 10 electrons over here, so I'm going to put 3d10, and then I'm going to go back to 4, and I'm going to put 4p6 itself, and there's the electron configuration for a bromide ion.